Okay, I guess I'll just get started. So yesterday I gave you the outline of interior point, and then I started discussing some optimization tools such as gradient descent, which is a first order method, meaning that it has access to some function f as well as its gradient on any query point. And we'd like to minimize the function f. Today I'm going to tell you about a second order method. This is called Newton's method. And in the second order method, you're not only allowed query access to the function and its gradient, you're also allowed query access to the Hessian of the function. Okay. And I will show you an analysis of Newton's method that will be relevant for interior point. Okay, so just a recap. Some things I want you to remember. So our goal with interior point was to minimize C transpose X such that AX is at least B. Okay, any LP can be written in this way. And we repeatedly approximately minimized f of lambda, okay, where f lambda of x is defined to be lambda C transpose X minus the sum I going from 1 to m of ln of slack of x at I, where the slack vector is defined as ax minus b. Okay. So we're going to use Newton's method to get better and better solutions to f lambda. Okay, so I want to tell you a little bit about Newton's method. So second order optimization, second order methods. We want to minimize some function f, which maps Rn to R. Okay. And we are given oracle access to f, the gradient of f, and the Hessian of f. And what I mean by that is, given a point x, there is some way for us to get our hands on f of x, the gradient of f at x, and the Hessian of f at x. Okay. So as usual, we start with some initial x init, let's say in Rn, and repeatedly apply some update rule. Right? And what we want to understand is how much does our error decrease as we do some number of updates. Okay. Setup clear for people? So this is Newton's method. We're at some current iterate, so we have some current x0 in Rn. Okay, and what's the update rule? And so we set x1 to be x0 minus the Hessian inverse applied to the gradient of f at x0. Okay, so that's going to be the update rule that we're going to analyze. Okay. And where does that come from? Well, remember what gradient descent did? Gradient descent wrote basically the first order Taylor approximation of the function plus some error bound that comes from Taylor's theorem. Okay? And then gradient descent just tried to minimize that expression. So what Newton's method is doing is it's taking the second order expansion, Taylor expansion of f, and it's minimizing that second order expansion, right? So Taylor's theorem says that, if you look at f of x1, well, let's say f of y, just some f of y, approximately up to some error that comes out of Taylor's theorem, this is equal to f of x0 plus the gradient of f at x0 dotted with y minus x0 plus 1/2 y minus x0 dotted with the Hessian of y minus x0. Okay. So this is what Taylor's theorem says in terms of approximating f by its second order expansion. And Newton's method is basically just assuming that this is an equality and then just tries to minimize the right-hand side. Okay, and the minimum of this right-hand side is exactly this if you do calculus. All right, so we just need to understand how well Newton's method does. So are there any questions so far? Okay. So let me write down a theorem. So again, for t in 0, 1, define xt to be x0 plus t times x1 minus x0, where by x1 I mean that x1, and by x0 I mean our the point that we're currently at. Suppose there exists an epsilon, a positive epsilon, such that for all t in the interval from 0 to 1, we have that the following is true. 1 minus epsilon times the Hessian of f at x0 is at most in the loner ordering. The Hessian at xt is at most in the loner ordering 1 plus epsilon, the Hessian at x0. I suppose that that's true. So remember, when we were analyzing gradient descent, it was a first order method. We only had access to the gradient. We couldn't actually compute the Hessian, but we had a promise about the Hessian, right? We were told that the Hessian is well conditioned. Okay, there's some small gap between its largest and smallest singular values. So again, for Newton's method, we need to have some kind of promise to say that Newton's method does well. Okay, and the promise that we're going to make use of is that the Hessian doesn't change too much on the line that connects x0 to the next iterate. Okay? Just to recap, when I say that a matrix A is at most a matrix B, remember that means B minus A is positive semi-definite. So suppose that's true, then I want to measure progress. And the way that I'm going to measure progress is that, okay, so is to say this. So the norm of the gradient of f at x1 under this, I'll say what this means in a second. Okay. So this is our progress theorem. Okay. So just a definition to make sense of the progress theorem. For a positive semi-definite matrix A, when I say the norm x sub A, that means, by definition, what I mean is x transpose AX square root. Okay. So we'll get into where this is going to why this is going to be useful for us in interior point in a second, but ignore this thing over here. It's telling us that the norm, and the norm is changing, okay, but the norm isn't changing too much because these matrices are very similar all across the line. In particular, the Hessian at x1 is very similar to the Hessian at x0. So pretend for a second that these are the same matrix. Okay. So in other words, these are the same norm. It's telling us that our new norm of the gradient is at most the old norm of the gradient times roughly epsilon. Okay. And the minimizer is when the gradient is 0, right? So we're getting closer to having 0 gradient. So that's how you should interpret this. Okay. Are there questions before I actually prove this? Okay. So let me give you a proof. I should confess I'm not an optimization expert, so I don't know the proper citation for this proof, but this is a proof that, anyway, Aaron Sidford was kind enough to share with me, so I'm just going to show you this proof. So first thing, I want to make an observation. What does it mean to say that 1 minus epsilon A is at most B is at most 1 plus epsilon A? Okay, how can I rewrite this? So that's the same thing as saying minus epsilon A, okay, is at most B minus A, is at most epsilon A. All right. And what does this mean? Remember what the definition of an operator norm is, right? So okay, this means, well, okay, so what does this mean? This means that for all x in Rn, minus epsilon x transpose Ax is at most x transpose Bx is at most epsilon x this is B minus A. And that's at most epsilon x transpose Ax. Okay. So in our case, we're going to be working with real symmetric matrices like Hessians. Okay. And the spectral theorem says when you have a real symmetric matrix, you can write a real symmetric matrix as U times lambda U transpose, where lambda has the eigenvalues, right? And these are going to be PSD matrices. So so lambda has some non-negative eigenvalues, and U is an orthogonal matrix. Okay. So when I talk about f of lambda, when I talk about, or I'm already using f, when I talk about some function g applied to A, what I really mean is take this decomposition and take g and apply it to lambda. And what I mean by that is apply that transformation to every single one of the eigenvalues. So then, if you do that, then what is x transpose Ax? That's just the L2 norm squared of a to the 1/2 x. Right? Same thing here. So now we can write y as a to the 1/2 x. And that implies that for all y, minus epsilon y transpose y is at most y transpose y, or what's x now? What's x? This implies that x is equal to a to the minus 1/2 y. Right. So this x is, we can write this as y transpose a to the minus 1/2 b minus a to the minus 1/2 y is at most epsilon y transpose y. And that's the same thing as saying that minus epsilon times the identity matrix is at most in the loner ordering a to the minus 1/2 b minus a to the minus 1/2, which is at most in the loner ordering epsilon times the identity. Okay, so when we go through the Newton's, you're going to see this come up in the proof of Newton's method. Oh, the question? Or? Yeah, so we're going to, so for Rf, it always is. I mean, we're going to apply this with f lambda. You can compute what the Hessian is. But yeah, so let's pretend it's invertible. Okay. Right. Another thing I think you can say is, for this inequality to even be true, it has to be the case that A and B have the same column space. Okay. And then what you could imagine is just kind of restricting, instead of A, really work with A times ux, where U has orthonormal columns that form a basis for that subspace, right? And then this composition of first you multiply by U and then you compose with F, that will then have be inverted. Well, okay, so sorry, but okay, for us it's invertible, so don't worry. Okay, so I'm going to kind of use these things interchangeably. Okay. Okay, so now proof of theorem, the analysis of Newton's method. So we can write delta of f at x1, or so not delta, the gradient of f at x1 as the gradient of f at x0 plus an integral from 0 to 1 of the Hessian right. So for example, if you just, I guess this is the fundamental theorem of calculus, or you can just view this as a zero-order Taylor approximation with explicit error. And this thing, so now we're going to use what x1 actually is. This thing is equal to the integral from 0 to 1 of the Hessian at x0 minus the Hessian at xt, x1 minus x0 dt. Oh, wait, sorry, this is not right. Oh, too many symbols. Okay, so I mean, I brought in the Hessian at x0, but then I killed it here. Okay, so this is just an identity. Okay. And then So, right, what's the thing that I want to bound? I want to bound this thing. And I'm going to plug in what I wrote for the gradients of f at x1 as that. So that implies that this thing is equal to the integral of that you can write the same norm. Okay. But now, because we know that the Hessians are spectrally similar along the entire line, we can replace this norm with the x0 norm, right? And pay at most a 1 over 1 minus epsilon. Right? So the Hessians themselves have this 1 minus epsilon, 1 plus epsilon, a gap. So if you take the inverses, you have a similar sandwiching inequality for the inverses, where on the right-hand side you would have 1 over 1 minus epsilon, and on the other side you have 1 over 1 plus epsilon. Yeah, question?
Yeah, I can see this equality there, where you multiply it on the left-hand side by Hessian f of x0, and on the right by the inverse. Right? So, yeah, multiplying is in general not commutative, so it is not the same as multiplying.
Did I write this wrong? Wait, hold on. So you're saying, so you mean if I expand this out, what do I get? Should I be more careful in expanding this out? So this is the integral. This is the integral from 0 to 1 of, so there's that inverse, so of the gradient. So that just gives you back that. And then there's minus the integral from 0 to 1 of. Oh, I see. Okay. Okay. Yeah. So, oh, sorry. This is minus. Is that what you were saying? Yeah. So this is minus this. Right. And this, by definition, this is exactly x1 minus x0. Okay. Okay. Good. So this thing here is at most 1 over 1 minus epsilon, where now I can switch the norm to the x0 norm. And also, I can bring the norm inside the integral, and that will only increase things as well. So this is at most 1 over 1 minus epsilon times the integral from 0 to 1 of the same thing. So Hessian squared, Hessian of at x0 minus Hessian at xt. This is a minus sign, sorry. Hessian inverse at x0. The gradient at x0 dt. And then I brought the norm on the inside with respect to x0 now. Okay. sorry, I guess this is, conceptually, there's not really a whole lot going on here, but it's just a lot of symbols. So, okay. But you should, yeah, definitely interrupt me if something looks fishy. Okay, and then now the claim is that this is just equal to 1 over 1 minus epsilon, the integral from 0 to 1, of the norm of Hessian at x0 to the minus a half, the gradient of f at x0. Okay, now a really long string of things. Okay. Okay, so it's kind of a nightmare. But basically, remember the definition of the A norm. It's just the square root of x transpose AX. Okay, so I promise you, if you expand this thing out as this transpose, this matrix times this, and you expand out this transpose times this big matrix times this, it's exactly the same thing. Okay? So I don't want to waste time. I mean, you can. It's going to be in the notes. You can verify it for yourself. Oh, do we have a scribe for today? Okay. Yeah, sorry. So yeah, feel free to just like take a picture with your phone or something, if it's too annoying to type. Yeah. So this is just writing things down explicitly and observing that they're actually equal. Okay, I'm not going to spend time on that. It's not something deep. Now, what do we know? We know that that's true, right? Which I said is the same thing as this being true, right? So what does that mean for us? We know that basically this whole matrix, call this whole matrix M, okay? By this, and basically this, if you just combine those two things, we know by star and double star that M minus epsilon I is at most M is at most epsilon I in the loner ordering. But here we have M squared. So that implies basically that M squared, well, certainly M squared is at least 0. M squared is a PSD matrix. And it's at most epsilon squared I. Okay. Good. So this thing is therefore at most 1 over 1 minus epsilon. The integral from 0 to 1 of the integral of this thing, f of x0 to the minus 1/2, f of x0 times epsilon squared identity. Yeah?
Sorry, could you just explain on the second, when you go from the first line to the second line, why you get 1 over 1 minus epsilon?
Okay. So So we could do the spectral theorem to this real symmetric matrix, right? And what do we get? We get U lambda, we get, forget about the inverse. Without the inverse, we get U lambda U transpose. So what does it mean to apply a function to a matrix? It means you take that decomposition and apply it to each of the eigenvalues. So what is the inverse of that matrix? It's U lambda inverse U transpose, right? And we knew that all the original eigenvalues between, so forget about the inverses, all the eigenvalues between these two matrices are the same up to 1 plus or minus epsilon. Oh. Yeah, I see. Maybe I see what you mean. 1 over 1 minus epsilon. Yeah, maybe I have to think about what you said. Maybe but okay, so worst case, I'm off by a square root. But in that case, the square root of 1 over 1 minus epsilon is basically the same thing as 1 over 1 minus epsilon. Right? Epsilon changes by a constant factor. I don't, so I'd have, yeah, let me not try and think through this on the fly. But at most, what you're saying would change epsilon by a constant. Okay. And now this is just, right, so we have the identity matrix here, a scaled identity matrix. So this is just the scaled L2 norm. Namely, it's the L2 norm scaled by epsilon because of the square root. So this is at most epsilon times the norm, just the normal L2 norm of this thing. These are different lines. Okay. But what's the L2 norm of a vector z? It's z transpose z. So when you do z transpose z on this, what you get is this. This is equal to epsilon times the square root of the gradient of f at x0 transpose, and then you get 2 minus a halves. So you get the Hessian f of x0 to the minus 1, and then you get the gradient again, which is exactly that. Oh, it's actually epsilon over 1 minus epsilon, right? Because of this 1 minus epsilon. Okay, so enough calculus. That's Newton's method. Okay. So now we have to go back to interior point. Okay. So let's remember that back to interior point. So we have our function f lambda of x defined to be this lambda c transpose x minus the sum I from 1 to m of ln of the slack. So if you do some calculation, this tells you that the gradient of f lambda at x is equal to lambda c minus A transpose the slack matrix at x inverse times the all ones vector. Okay. Remember, this is, forget about the inverse. The slack matrix is the one where you just take the slack vector and you write it on the diagonal. This is a diagonal matrix. This is the all ones vector. And if you go and calculate the Hessian, this thing doesn't depend on C at all. This is just A transpose Sx minus 2A. Okay? Okay. So So remember that progress in Newton's theorem is all related to this norm, right? So that's how we're going to measure our progress in IPM. So good. So let me give some definitions. So remember that we start off with some initial lambda. I'm going to go back to this toward the end of lecture. We start off with some initial lambda naught, right? And we assumed that we had an approximate optimum for lambda naught. And then we moved on from lambda naught to lambda 1, which was very slightly bigger. And then we used our approximate solution for lambda naught as a starting point for Newton's method for lambda 1, for f sub lambda 1, right? We want to minimize f sub lambda 1. We run a few Newton steps, and then now we hope that we get to something that's not so bad for f of lambda 1. And then we increment to lambda 2, et cetera, right? So what is not so bad and approximately minimizing mean? Well, I mean, Newton's method tells us one way how we can measure progress. So that's going to be our way of saying that it's a good solution, right? So we're going to say, we're going to define the centrality of x for f sub lambda k as delta sub k of x is the gradient of f sub lambda k at x under the norm specified by the Hessian inverse at x. Okay. So suppose that x were actually the minimizer of f lambda. What could you tell me about the centrality? It's 0. Because if you're actually the minimizer, the gradient is 0, right? So this is some measure that tells you how close you are to, in a funny norm, how close you are to the minimizer. Okay? Let me make two more definitions. Definition. X is coarsely or finely central for f lambda k if delta k of x is at most 1 over 100. And also x is coarsely central if delta k of x is at most, say, a third. Okay, so what we're really going to say is, look, for lambda k, we have in our hand a finely central point. And then what we want to say is, if lambda k plus 1 is not too much bigger than lambda k, that finely central point for lambda k will still be coarsely central for lambda k plus 1. Right? Which means that our measure of progress in Newton's theorem, our initial error under that funny norm is a third. And we want to make it finely central again. We want to get back from coarsely central to finely central. We want to get from a third down to 100th. But that's just a constant number of Newton steps, right? As long as our Hessians are behaving well, we're going to roughly have our error in every step or in every constant number of steps. To go down from a third to 100 is just a constant number of steps. Okay, so IPM is going to always keep a finely central point in hand, increment lambda, run a few Newton steps to turn that coarsely central point into being finely central again. Okay, so that's where we're going. Are there questions about where we're going before we actually do some calculations? And we have to understand how much are we, so I think I mentioned at some point that we're going to be able to increment lambda by a 1 plus 1 over root m factor in every step as we go from k to k plus 1. That 1 plus 1 over root m is going to come from the fact that we want to maintain coarse centrality. We need to understand how big can we give an increase to our lambda to make sure that a finely central point is still coarsely central. Yeah?
So I just forgot the quantifiers.
Yeah.
Epsilon doesn't depend on lambda, does it?
Epsilon,
When we had the
it will, so the epsilon that we're going to get at the end of the day will be just some small constant.
okay. So it doesn't depend on lambda.
Right, but I mean, so when we apply Newton's method, our f is actually f lambda k for some k, right? So it's okay if the epsilon does depend on, I mean, the function, because we're doing Newton's method over and over and over again in the sense that we have one f, we apply Newton's method. Now we change f. Now we run Newton's method again. As long as the epsilon for each instantiation of Newton's method is some fixed thing, that's fine. Okay. Okay, so first off, here's one thing I want to understand, which is how does the Hessian change as you change x? Right? Because if you look at Newton's method, it says that the Hessian shouldn't be changing too much on the line that you're optimizing over, right? So if I'm going to have any hope of controlling that, I need to understand when I vary x, how is the Hessian changing? Now remember, the Hessian, we said, is just this thing, f lambda of x is A transpose Sx minus 2a. Right? It doesn't depend actually on lambda at all. So really, the only thing it really depends on are the slacks. Right? Because if you take a spectral decomposition of this matrix, the eigenvalues that you're getting correspond to the, what do I want to say? Yeah, so okay, so right, so okay, so the only matrix that's changing as you vary x is the slacks. So I want to understand how do the slacks eigenvalues change as you change x. Okay. So I want to understand for which x prime do we have the slacks don't change by much. 1 minus epsilon s of x is at most s of x prime is at most 1 plus epsilon s of x. Okay. First, let's understand this before we continue. So what do I want here? I want 1 minus epsilon right. I want 1 minus epsilon times the identity actually let me just do what I said before. So let me subtract slack of x from both sides. I want minus epsilon slack of x to be at most slack of x prime minus slack of x to be at most epsilon slack of x. So minus epsilon times the identity is at most slack x inverse slack x prime minus slack x at most epsilon times the identity. Okay. And so now all of these things here are diagonal matrices, right? So the largest eigenvalue, so what do we want? We want that all the eigenvalues in magnitude are at most epsilon of this matrix. It's a diagonal matrix. That means we want all the entries in the diagonal to be at most epsilon in magnitude. So this is the same thing as saying that the infinity norm of the slack matrix Sx prime minus Sx, this is now the slack vector, is at most epsilon. Okay? So to understand when this holds, it's enough to understand when this holds. Okay? Well, what do we know? Well, we're going to do something very loose right now, which is that we're just going to bound the infinity norm by the L2 norm. So this thing is at most slack inverse Sx prime minus Sx L2 norm. Okay. And again, this is equal to, I think we've seen this trick before. What's the slack x prime minus slack x? What is that? What is this? What is the slack at x? What's the definition of slack? So remember in our original LP, we're trying to minimize C transpose x subject to AX is at least B, right? So the slack is how far away is each constraint from B, from BI, right? So the slack vector is just AX minus B. That's the definition of the slack vector. So the B's cancel here. So this is equal to Sx inverse A x prime minus x. And really, actually, remember that x prime. I shouldn't have. I should have really just said xt. I'm sorry about that. So imagine in your mind x prime is actually xt, which is, if you remember, it's t times x. It's x0 plus t times this x1 minus x0 business, right? So we're imagining that we're looking at how the slack changes along the line of optimization in Newton's method. That's the thing we need to understand Hessians of to be able to apply the theorem from Newton's method. So if you just remember what this thing is, this is minus Hessian inverse times the gradient. This is equal to kind of t times slack x inverse A Hessian x inverse gradient f L2 norm. And this is just equal to t times now the gradient of f at x0 So what is, okay, so good. So this is the Hessian. I mean, basically this is going to be exactly the centrality at x0. So this is, sorry, I started switching between x and x0s in the middle, but. So the point is, if you're doing a Newton step starting at a point x, and x prime is anything along the line toward the new iterate in Newton's method, then the good. This error is at most the centrality, okay, which we want to be less than epsilon. Okay. So the point is, if x is actually, so right, we updated lambda, and our finally central point became coarsely central. I haven't proven that yet. But the point is, it is coarsely central, which means that the centrality at that point is at most a third. Okay? So this is at most, let's say, t over 3. Okay. So in particular, we are satisfying we're satisfying the conditions of Newton's method where epsilon's a third. I guess that's what I should have said. I see a lot of worried faces.
Can you see that again and explain why we start, when we update lambda, we start necessarily with coarsely central?
Oh yeah, I didn't, okay, so yeah, I didn't prove that yet. So suppose that we have a coarsely central point now for f lambda k plus 1, and we want to make it finely central. What are we going to do? We're going to run Newton's method and hope that the error, gets killed down back to a 1 over 100 to make it finely central. And in order to apply Newton's method to say that we're knocking down the error by a constant factor in every iteration, we need to make sure that that epsilon from the conditions of Newton's theorem is something that's at most a constant, like at most a half or something, right? Because we're killing the error by epsilon over 1 minus epsilon fraction in every single step, right? So to make sure that epsilon over 1 minus epsilon is non-trivial, epsilon had better be strictly less than a half, right? So what I'm showing you is that the rate of change of the Hessian does satisfy that property, where epsilon is the centrality of the point. And the centrality is at most a third because we started off being coarsely central. Okay. Any other questions? Don't be shy, you can feel free to ask me anything. Think about it if you want to ask me anything as I start erasing the other board. So yeah, you're right. Kind of the thing that we need to do now is we need to verify that it's actually the case that if you take a finely central point for lambda k, it will be coarsely central for lambda k plus 1, right? Then you could plug in this argument and say Newton's method will make it finely central in a constant number of iterations. So, oh yeah. That's right. Right. So, very good. So what did I? Good. So okay. So you're saying the Hessian. So what is the Hessian? So the Hessian is this A transpose Sx minus 2A. And the Hessian at x prime is now A transpose Sx minus 2 prime A. And we want to say that these things are spectrally similar. We want that for all x, basically Ax transpose, well, x transpose A transpose Sx to the minus 2 Ax. We want this to be up to 1 plus epsilon, the same thing as, oh, I shouldn't use x here because I already have x's. For all z's. This thing should always be close to z transpose A transpose Sx prime minus 2 Az. That's what we want, right? So what is this thing? This thing is the it's Sx inverse Az L2 norm squared. And this thing is Sx prime inverse Az L2 norm squared, right? Yeah, so now it's clearer. So the point is, if these things have eigenvalues that are all close to each other, then on any vector, in particular the vector Az, the norms will be roughly the same. Sorry for, I guess I was hand waving a little bit, but thanks for keeping me honest. Yeah, so really, to say that the Hessians are spectrally similar, you can just focus on the slack matrix. Okay, yeah, any other questions? Okay, so let me not erase this yet. Okay. So actually, if you don't mind, I want to erase this as late as possible. So are people, I'm going to erase this now. Are people okay? So that board over there, the last board, says that if we start with a coarsely central point for lambda k plus 1, we can make it finely central in a constant number of Newton steps. Okay. So assume that the k centrality of some of our approximate minimizer x tilde of lambda k is at most 1 over 100. So assume we have a finely central point for lambda k. So now the question is, how much bigger? Remember that as lambda goes to infinity, solving f lambda is getting closer and closer to solving the actual LP we care about. So we want to make progress. We want lambda k plus 1 to be as big as possible. But if we make it too big, then this point won't even be coarsely central anymore. We'll fall off the central path. So the question is, how much are we allowed to increase lambda k by to get lambda k plus 1 such that x tilde lambda k will still be finely central for f lambda k plus 1. So, I'm sorry? Yeah, coarsely. Thanks. So let's say that we're going to do a multiplicative increase. So let's say that lambda k plus 1 is equal to 1 plus some factor alpha times lambda k. Right? And we want to understand how much does that change delta k by. Okay. So delta k plus 1. So I'll just write it over. I'll just write the irrelevant stuff here. So the gradient of f lambda at x is lambda c minus a transpose s inverse times the L1's vector, and the Hessian is a transpose sx minus 2a. Okay, so that's all we're going to need to remember. So let's compute this thing. Let's look at sx plus 1 of x lambda. So this is our finely central point. X tilde lambda k is our finely central point for lambda k. And we want to understand now its centrality measure for k plus 1. What is that? That's equal to, well, let's just do the definition. That's equal to the gradient of f at lambda k plus 1 at the point of the Hessian. Well, the Hessian doesn't depend on lambda at all, right? The Hessian is just a transpose xx minus 2a. So okay, that's the definition of centrality. And then now let me write down what the gradient is. The gradient is now lambda c, lambda k c. Well, lambda k plus 1 is just 1 plus alpha times lambda k, right? So lambda k times 1 plus alpha times c minus a transpose sx inverse L1's vector times that same thing. Okay. Okay, and then now I want to basically add and subtract alpha times this matrix. So this is equal to 1 plus alpha lambda k c minus a transpose sx inverse L1's vector. But then we just subtracted alpha times this, so we better add alpha times it back, plus alpha times the same thing. And then, the usual Hessian inverse over there. And then now we do triangle inequality. Right? So what is this? Hopefully this is now, it's clear what I'm doing here. Okay, what's that? Yeah, right. Yeah, delta Clay if you include the norm with the Hessian inverse. But yeah, the point is, this is just the gradient at lambda k. So we can do triangle inequality and say, look, this is at most 1 plus alpha times the centrality measure at lambda k, or the centrality measure at k is how I defined it, of x tilde lambda k. And that thing is at most 1 over 100. So that's fine. Plus, now we have an alpha out here. A transpose Sx inverse, 1 vector. And now let me write again. This is A transpose S x tilde lambda k. Minus 2 A inverse. OK, so this part is fine, right? We're trying to make sure that this thing is at most a third. As long as alpha is tiny enough, the 1 over 100 is going to become 1 over 50 or something. We don't really care about that. But then we need to understand this thing here. All right, so we need to understand this thing. So this thing, so what is it equal to? Well, let's expand what it means to take a matrix norm like this. This is equal to 1 transpose Sx inverse. This is all x. X here, remember, is x tilde lambda k. All these x's are x tilde lambda k. X tilde lambda k. And then A and then A transpose S x tilde lambda k minus 2 A inverse. And then the same thing, A transpose Sx tilde lambda k all at once. Okay, looks like a mouthful, but I claim that there's something special about this matrix. Okay. There's a minus 1 here. Okay, so whether or not you see this, I guess, will depend on how much you remember your linear algebra. Okay, it's not necessarily the identity, because right. Okay, good. So if everything were full rank, it would be the identity. Yeah. In general, what this is it's a projection matrix. Okay, this is the so this red thingy is equal to the projection, orthogonal projection onto the column space of S minus 1 x tilde lambda k at A. Okay. So in general, if you want to project, so the projection onto the column space of A is A transpose A inverse, and then put an A here. A transpose A. So, I mean, the best way to see that is, well, you can see it by, for example, taking the SVD of A, and when you expand this thing out, you get UU transpose, where U is the matrix with left singular vectors. But what does that tell us about this thing? This implies that this yellow boxed thing, right, is at most 1 transpose 1 square root, which is root m. Okay. So really, this thing, so what we've shown, at the end of the day, what we've shown is that delta k plus 1 at x tilde lambda k is at most 1 plus alpha delta k x tilde lambda k plus alpha root m. Okay? We want this thing to be less than a third. And we said that this thing was coarsely central, so this was at most 1 plus alpha over 100 plus alpha root m. We want this thing to be less than a third, so choose alpha to be something like 1 over root m, 1 over 10 root m or something. And then it's coarsely central. Okay? So that's basically it. We can increase lambda by a multiplicative 1 plus 1 over root m at every step. If you remember, I told you that somehow we get an initial point that's really good for lambda initial being roughly exponential and minus the precision. And we're done when lambda gets to be as big as something like m times exponential in the precision, right? So I think I mentioned this last class. You can look at the notes. But the point is, this tells us we can take roughly root m iterations of step 5 from last time, where we have to keep increasing lambda. We have to increase lambda roughly root m times L times, where L is the precision. So that's it for, I guess, the main part of interior point. It all just now boils down to how do you get the initial finely central point, right? Or even the initial coarsely central point. You can make it finely central with Newton's method. Yeah. Oh, question?
Sorry. So what's the best result that we have for this?
So instead of square root m times L, you can get square root rank of a times L.
Was that the presentation by
Aaron Sidford. Yeah. So that was a recent paper by Sidford and Lee. And I'll say,
Did they bring it to rank? Is that what they do?
huh? Yeah. They turned the square root m into square root rank of a. And the basic idea behind, so there's a lot going on there, but the highest level, most basic idea is if you look at the barrier function that we're using, it's minus the sum over I of log of slack I, which is kind of weird because this means that if you repeat the same constraint over and over and over again, it's getting weighted more and more in the barrier, right? But the optimization problem you're solving actually hasn't changed at all. So what their algorithm does is at every point it maintains kind of a weight vector so that you use the same barrier but a weighted version of that barrier where every constraint is weighted by a certain amount. And the amount that you have to weight each constraint by in that barrier function depends on some geometric considerations. Okay, so that's the heart of their change. And then there's a lot, then how do you come up with this weight vector and how do you maintain it and analyze things, et cetera. But the new thing that changed to get down to root rank was that they used some kind of weighting of the constraints in the barrier function. Does that make sense?
Can you explain again why some constraints are more than others?
Oh yeah, right. So the point is, the barrier we're using is, right, minus some I from 1 to m of ln of slack of xi, right? So what are the slacks? You have, what is the constraint? The constraint matrix is ax is at least b. That's the constraint, right? So what is a slack? A slack is the ith row of a dotted with x minus bi. So suppose you just have the same constraint. Suppose someone just gave you the LP with the same constraint written 1,000 times. You're going to sum it 1,000 times here. But that's sort of weird, right? Because the constraint only matters once. So they have some way of weighting the constraints in this barrier function. So they actually have a minus sum over I weight I. And they have some way of figuring out these weights that guarantees faster convergence.
And those weights would stay constant.
I think they even changed the weights over time as well. And when we had to look at how does the centrality change as you change the lambdas. They also have to look at how does it change as you change the W's as well. So they also need to be able to compute these W's efficiently because you want a fast algorithm at the end of the day. Yeah. So I don't know all the details of their paper. My understanding is that there was an existential theorem due to Nesterov, or maybe Nesterov and Nemirovsky, I'm not sure, that showed that there exists a weight vector. But it was not algorithmic at all. And they show that they can actually algorithmically efficiently maintain some weight vector that does close to as well as that existential result. Okay. So I want to say something. I just want to close this lecture with how you actually start off. So again, this is going to be down to precision issues, so I don't want to give all the calculations, but the basic idea is, so how to start the IPM, right? We need to have some x tilde lambda 0 to start it off, which is coarsely central or finely central initially. So the point is, so first what we're going to do is we're going to alter the LP to be min C transpose X plus capital N times Z. I'll say again in a second what this is, such that AX plus the all ones vector Z is greater than or equal to B. Okay. Has an obvious, and Z has to be at least 0. Oh, let me put, there's some more. Also, 0 is at most, Z is at most 2 to the L plus 1, and negative 2 to the L plus 1. All ones vector is at most, X is at most 2 to the L plus 1, all ones vector. So I'll put a link, I'll put a reference in the notes, but you can show that if n is big, if n is like exponential in the precision, let's say, 10 to the L or something, or 100 to the L, then original LP bounded and feasible implies that LP prime optimum must have Z equals 0. Okay. So you can prove this kind of theorem by looking at various precision calculations. And then the point is, so now if you could actually just solve this one, well, the optimal solution has Z equals 0, so you've actually solved the original LP. Okay. And in the original LP, you can show that any solution has to have bounded precision anyway. Okay. So now we just need to solve this thing. I'm just giving you a sketch of what's going on. Okay. So this is LP prime. So LP prime has an obvious interior point. X prime, which let's write that as x comma z. You can set x to be 0, and you can set z to be the L infinity norm of B. Right? So that's an interior point. Are we done? Yeah, finally central. What's lambda? And is it finally central for that lambda? Who knows? So we're not done. But then there's one last trick. We don't just need an interior point. We need a coarsely central interior point for some lambda, right? So what are we going to do? Here's now a funny thing we're going to do. Set lambda to be 1. Okay. Now let's look at the gradient of f of lambda at this x prime. Remember, the gradient is equal to lambda times c minus, I think slack inverse, right? A transpose slack inverse all ones vector. Right? When are we optimal? We're optimal when the gradient is 0. So here's the funny thing we're going to do. Okay, sure, here's the funny thing we're going to do. So x prime is perfectly central for a different cost function. So this is lambda is equal to 1, right? So it's perfectly central for the cost function A transpose xx prime inverse all 1. Right? OK? So now, right, the gradient is 0 now for this cost function. That's not our actual cost function, but the gradient is 0 for this cost function. So what do? So now we have a point which is perfectly central for some cost function. You can basically run all the update steps I told you in reverse. Instead of incrementing lambda by a little, you decrement it by a little. And you run Newton's method, and then you keep refining going down in lambda until you get to a very, very, very tiny lambda, exponentially small in the precision. And now what do you have? You have a point that's finally central near the analytic center. And then what you show is that when you have a point that's finally central near the analytic center, you can basically just switch the cost function to whatever you want, and you'll still be finally central. Because once lambda is that tiny, the cost function basically doesn't matter anymore. Right? So once lambda is that tiny, you then switch over the cost function. You'll still be finally central. And then you run everything I told you in the forwards direction. Now run everything in reverse to get an approximate analytic center, which is basically, finally central for any cost function of bounded precision. And now that you have that, well, now you run things forward. Okay, so that's everything. Does that make sense? Okay. So that's it, I guess. So I'll see you Tuesday.